Hey friend, tonight we'll explore how the universe might actually store information, how reality itself could be made of data, and how every particle, every star, even you, are part of that vast memory. Let's begin. Chapter 1. Information is physical. When we speak about information, we usually imagine something abstract, words on a page, bits on a screen, or thoughts in a mind. Yet physics teaches us that information is not a metaphor. It is something that lives within the fabric of the universe itself. Every particle, every photon, every magnetic spin carries with it a trace of what it has been and what it can become. The recognition that information is physical marked one of the most profound shifts in modern science, turning an intangible concept into a measurable quantity woven into the laws of nature. In classical physics, the state of a system is defined by its measurable properties: position, momentum, charge, and so on. If those quantities are known with perfect precision, then in principle the system's future can be calculated exactly. Information, in this classical sense, is the full description of a system's state. But information was long treated as a bookkeeping tool for humans, not as something that mattered to the universe itself. That changed in the mid-20th century when communication theory and thermodynamics began to converge. Claude Shannon, working at Bell Labs in the 1940s, defined information in mathematical terms. For him, information measured uncertainty. The less predictable a message, the more information it contained. A random coin flip carries one bit of information because it could turn out either way. But Shannon's theory was intentionally agnostic about meaning or physical form. Information could be written in ink, encoded as electrical signals, or stored as holes in magnetic tape. The medium didn't matter. What no one yet realized was that the physical medium matters far more than it seems. In 1961, physicist Rolf Landauer made a deceptively simple statement: information is physical. He argued that processing or erasing information requires physical energy, and that energy exchange obeys the same thermodynamic laws that govern heat and motion. According to Landauer's principle, erasing a single bit of information always produces a small but unavoidable amount of heat, dependent on the system's temperature. The message was revolutionary. Computation was not a purely abstract operation. It had a cost measured in energy. From that moment, information became inseparable from physics. This insight also solved a long-standing paradox. In the 19th century, James Clerk Maxwell imagined a tiny demon capable of sorting fast and slow gas molecules to decrease entropy without doing work, apparently violating the second law of thermodynamics. For decades, scientists struggled with this puzzle. Landauer's work finally revealed the answer. The demon's act of storing and erasing information about molecules carries an unavoidable energy cost. Once information is accounted for as a physical entity, the second law stands firm. The demon cannot cheat nature, because thinking itself consumes energy. By embedding information into thermodynamics, physics extended its reach from matter and energy to knowledge and memory. This marriage birthed a new perspective on reality, one that John Archibald Wheeler captured in his famous phrase, "it from bit." Wheeler proposed that every particle, field, and space-time event ultimately derives its existence from binary choices, yes or no answers registered by the universe. Matter, energy, and geometry are not fundamental on their own. They emerge from acts of information. The universe, in this view, is not a stage upon which information happens. It is the information evolving through interactions that continually record new facts about themselves. Quantum mechanics gave this picture its depth. In the quantum realm, the act of measuring a system does not merely reveal information, it changes it. A particle's state is described by a wave function containing probabilities for every possible outcome. When we measure it, the wave function appears to collapse into one definite state, and the probabilities instantly update. This is not because the system hides a secret classical truth waiting to be discovered, but because reality itself is built from these informational transitions. The measurement imprints information onto the observer and the environment, forming a new physical fact in the universe's record. In this sense, the quantum world is an information engine operating under strict conservation rules. Quantum theory is linear and reversible, meaning that the total information encoded in the wave function never disappears. It only transforms and spreads. Even when systems seem to lose coherence, the information is not destroyed. It disperses into entanglement with other systems. This principle of conservation of information lies at the heart of nearly every modern debate in theoretical physics, from black holes to cosmology. But what does it mean for information to have a physical embodiment? Consider a single bit. In a classical computer, a bit might be represented by a transistor, voltage high for 1, low for 0. The configuration of atoms and electrons gives that bit existence. Similarly, in nature, any stable distinction between two states, north or south, magnetic spin, photon polarization left or right, constitutes a bit. The difference between states carries entropy, and entropy measures missing information. The second law of thermodynamics is thus also a law about the flow and transformation of information. Closed systems evolve toward configurations with more possible microstates, because those states represent the loss of distinguishable information. At the quantum level, the concept extends to qubits, quantum bits that can exist in superpositions of 0 and 1 simultaneously. When a qubit interacts with others, it stores information not in discrete symbols, but in the complex amplitudes that describe correlations. A pair of entangled qubits, for example, shares information that is not localized in either one. It exists only in the relationship between them. This relational nature of quantum information is profoundly different from classical storage. It suggests that the universe's informational fabric is not composed of isolated facts, but of patterns of correlation, networks of meaning embedded in probability. Landauer's principle, Shannon's equations, and the behavior of qubits together imply that the universe obeys what physicist Seth Lloyd later called the ultimate physical limits to computation. Every particle interaction is a kind of information processing step. Every second, the observable universe performs an unimaginable number of elementary logical operations. Each collision, emission, and absorption rewrites the cosmic memory. From this viewpoint, the universe is not a computer built by someone else. It is a self-computing entity perpetually evolving its own informational state. The physicality of information also sets boundaries on what can be known. If erasing a bit costs energy, then perfect knowledge of an entire system would require infinite resources. Nature maintains balance by ensuring that some information is always inaccessible or entangled beyond retrieval. This limit preserves the uncertainty principles at the heart of quantum theory. The impossibility of cloning an unknown quantum state, for instance, arises from the linearity of information. Duplicating perfect knowledge would violate conservation laws. The same restriction ensures that information cannot travel faster than light, protecting causality across space-time. When scientists examine processes as different as DNA replication, photosynthesis, or black hole evaporation, they now ask not only what happens, but how information moves and transforms during those events. The double helix stores genetic information in molecular structure. Photons transfer quantum coherence across pigment molecules in a leaf. Black holes encode the details of infalling matter on their event horizons. These are not metaphorical parallels. They follow the same principles of informational bookkeeping that govern all physical change. Entropy and information, order and uncertainty, are two sides of the same coin. The informational view of nature reshapes even our understanding of energy. In classical thermodynamics, energy was primary and entropy a derived quantity. In the quantum informational view, energy and entropy are complementary expressions of information. Energy describes how rapidly information can change. Entropy measures how much of it remains hidden. Temperature becomes a rate of information exchange between systems. When two bodies come into thermal equilibrium, what they truly share is not heat, but informational symmetry. Their microscopic states become indistinguishable. Nowhere does this connection become more dramatic than in the study of black holes. According to Stephen Hawking's early calculations, black holes radiate and eventually evaporate, apparently destroying the information about what fell into them. Such loss would violate the reversibility of quantum mechanics and challenge the core of physics. Decades of research have shown, however, that information is not lost. It is encoded in subtle correlations within the outgoing radiation or preserved on the event horizon itself. This realization led to the holographic principle, which proposes that the information content of any region of space is proportional not to its volume, but to the area of its boundary. The boundary, in effect, serves as the universe's hard drive, storing every detail of what happens within. Even space-time geometry seems to emerge from patterns of entanglement. In certain quantum gravity models, connecting two regions of space-time corresponds to sharing quantum information between them. If those correlations vanish, the geometry itself unravels. This suggests that the fabric of space may not be a background arena at all. It may be the large-scale manifestation of microscopic information links. The gravitational field becomes a code, and curvature becomes compression or expansion of data. From the smallest particles to the largest cosmic structures, everything that exists can therefore be described as a configuration of information encoded in quantum states. Matter is information with persistence. Radiation is information in transit. Space-time is the geometry that arises when information connects across distance and time. Conservation of information ensures the coherence of the universe, the reason why cause precedes effect and why history does not simply vanish into oblivion. This perspective also alters how we think about observation and consciousness. If every interaction that records a fact constitutes a physical act of information exchange, then observation is not a mystical intrusion, but a natural process. When a photon hits your retina, it changes molecular states in your eyes and neurons, embedding its history in a cascade of physical transformations. Your awareness of that event is the highest level of a chain that began with quantum information interacting with biological matter. In a literal sense, You are made of the universe's information, remembering itself. Understanding that information is physical brings humility. It tells us that knowledge is costly, that memory leaves traces in energy and entropy, and that forgetting is as real as burning fuel. It also opens hope that the order we see around us is not accidental. The laws of physics maintain a delicate balance. No event can happen without updating the universe's ledger. No bit can vanish without compensation elsewhere. The cosmos behaves like a perfect accountant, every interaction recorded, every fluctuation balanced, every transformation conserved. In daily life, the idea that information has physical weight is easy to forget. Yet every email stored, every neuron firing, every beam of sunlight scattering off a surface participates in this grand informational dance. When light bounces off a table, it encodes microscopic details of that surface in its reflected waves. Those photons disperse into space, carrying traces of the table's structure forever. In principle, if we could gather every photon, we could reconstruct what the table once looked like. Reality continually writes and rewrites itself in such scattered signatures. The next chapters will explore how this informational continuity spans time itself, how entanglement connects moments that appear separate, and how the universe preserves its memory across eons. But even here, at the foundation, we can sense the profound implication. Information is not merely about the universe. It is the universe. Every quantum state, every field excitation, every line of energy and matter participates in an unbroken conversation of data exchange that began at the Big Bang and has never stopped. As you let these ideas settle, consider that the thoughts forming in your mind right now are part of the same informational chain. Your neurons shift electric charges, molecules release energy, and patterns of information flow through your brain, momentarily mirroring the deep logic of the cosmos. You too are a processor of the universe's code, reading and rewriting its symbols with every heartbeat and breath. And now, as the day fades and the world grows quieter, you can allow that vast continuity to bring you peace. The universe keeps its balance perfectly. No bit is ever truly lost. The information that shapes stars, atoms, and thoughts flows gently onward, indifferent to worry and untouched by haste. Let your mind rest within that certainty as the endless computation of reality continues softly around you, humming with the quiet logic of everything that has ever been. Chapter 2. The universe as a quantum memory. If information is physical, then the universe must have a way of storing it. Every event that has ever taken place, every photon that has scattered, every atom that has moved from one position to another, each leaves behind traces written into the structure of reality itself. The cosmos in this light is not just a vast expanse of matter and energy, but an unfolding record of its own evolution. It remembers, though not in the way human memory does. The universe's memory is distributed, subtle, and deeply quantum in nature. In the classical world, memory seems straightforward. We record events in photographs, books, or digital drives, each requiring some stable physical medium. These memories can degrade, but they exist as tangible encodings of past states. On the cosmic scale, however, the concept becomes far more profound. The universe itself has no external storage device. Its memory must be written into its very fabric. Every atom and field configuration is part of an ongoing computation that not only evolves forward, but also contains within it the imprints of everything that came before. Quantum mechanics provides the mechanism for this cosmic record. According to the principles of quantum theory, the state of any system is described by a wave function, a mathematical object that encodes all possible configurations of the system and their probabilities. The evolution of this wave function is unitary, meaning that information about its initial state is preserved at every moment of time. Nothing truly disappears. It only becomes more complexly entangled with its surroundings. This unitarity is one of the cornerstones of modern physics, ensuring that the total information content of the universe remains constant even as its form continuously changes. At first glance, this principle seems abstract, but it underlies everything from the persistence of atomic structure to the formation of galaxies. When two particles interact, their wave functions become entangled, a deep quantum connection that links their properties no matter how far apart they later move. Entanglement ensures that a record of their interaction remains encoded in the combined system. Even if one particle travels across the universe, measuring it can reveal correlations that point back to the moment of entanglement. In this way, quantum processes generate threads of memory that stretch across space and time. Entanglement is therefore not just a curiosity, it is the mechanism by which the universe remembers itself. Each interaction between particles leaves behind correlations that, in principle, could be traced backward to reveal their history. We cannot access that information directly because it becomes distributed across an enormous number of degrees of freedom. But according to quantum theory, it never vanishes. The universe's apparent forgetfulness is not true loss, but a matter of inaccessibility. The record remains, encoded in relationships so intricate that they blur into what we perceive as randomness. This realization reframes our understanding of time. In a purely classical sense, the past is gone, its configurations no longer exist. But in quantum physics, the information describing the past still exists in the present state of the universe. It is merely entangled, dispersed, and hidden. The arrow of time arises not from destruction of information, but from its diffusion. The more the universe expands and evolves, the more entangled its parts become, and the harder it is for local observers like us to reconstruct the original order. Entropy increases, not because information disappears, but because it becomes too widespread to retrieve. When we think of memory, we imagine something like a file that can be opened and read. The universe's memory is different. It is holographic and collective, existing in patterns of correlation among countless particles and fields. Each fragment of the universe contains partial information about the whole. This concept is beautifully illustrated by the holographic principle, a profound idea emerging from black hole physics. It proposes that the total amount of information in any region of space is encoded on its boundary surface like a cosmic hologram. Every point on that surface stores information about the three-dimensional world within, much as every fragment of a holographic plate contains the entire image, though at lower resolution. In this holographic sense, the universe is an enormous quantum archive. Space and time themselves might be emergent from the way information is stored and processed across its boundaries. When we look into the night sky, we see photons that have traveled for billions of years, carrying imprints of their origins. The cosmic microwave background, the faint afterglow of the Big Bang, is a perfect example of such memory. Those ancient photons preserve the density fluctuations of the early universe. Tiny differences in temperature, that seeded galaxies and clusters we see today. They are not just light from the past. They are the universe remembering its own beginning. The persistence of quantum information becomes even more striking when we consider black holes. In classical general relativity, anything that crosses a black hole's event horizon is lost forever. But quantum theory insists that information cannot simply disappear. This apparent contradiction, known as the black hole information paradox, has driven decades of research. The most widely accepted resolution now suggests that information about what falls into a black hole is somehow encoded on its surface or in the radiation it emits as it evaporates. The universe, even in its most extreme conditions, seems determined to keep its records intact. This perspective changes how we think about causality and determinism. In quantum mechanics, the evolution of the wave function is fully deterministic in the sense that knowing the current state allows the future to be predicted. Yet the randomness of measurement outcomes means that for us, as observers, each moment appears uncertain. Still, the total wave function contains a complete history, both what has happened and what could happen, woven into its complex structure. The universe evolves like an enormous quantum algorithm, one that constantly encodes its past interactions while projecting new possibilities forward. One of the most fascinating consequences of this framework is the concept of quantum Darwinism. In this idea, proposed by physicist Wojciech Zurek, the environment acts as a witness that records the states of quantum systems. When an atom emits light, that light interacts with countless other particles, effectively copying information about the atom's state into the environment. This repeated broadcasting allows multiple observers to independently measure the same property, such as the position of a macroscopic object, and agree on what they see. Classical reality, in this sense, emerges from the universe's distributed memory. It is the shared information that survives repeated copying through the environment. Our everyday perception of stability, the fact that objects persist from one moment to the next, arises from this continuous information recording. A chair remains a chair not because it is frozen in time, but because the correlations among its constituent particles and the surrounding environment maintain a consistent pattern. Those patterns act as the memory of the chair's identity. When you look at it again tomorrow, the photons reflecting from its surface will carry the same encoded information, reinforcing that memory. What we call persistence is, in fact, an ongoing act of quantum remembrance. The cosmic scale amplifies this logic to unimaginable proportions. The interstellar medium retains traces of supernova explosions in the form of enriched elements. Planetary orbits preserve the dynamical memory of their formation from rotating disks of dust and gas. Even the large-scale structure of the universe, its vast filaments and voids, reflects the imprint of primordial quantum fluctuations stretched by cosmic inflation. The present universe is not a random configuration, but a coherent memory of its entire evolution, encoded in the arrangement of matter and energy at every scale. Yet this memory is not static. Quantum information constantly flows, transforming the universe's record as new interactions occur. Because information is conserved, every new event must be integrated into the existing fabric without erasing what came before. The universe, in this way, behaves like a perfect memory device. It never forgets, but it continually rewrites its story in a denser, more entangled language. Each moment adds complexity, creating a deeper and richer tapestry of correlations. This continuous rewriting implies that the future is not entirely independent of the past. Some interpretations of quantum mechanics suggest that correlations can extend not only across space, but also through time. In time-symmetric formulations, the universe's present state contains information flowing from both its past and its future boundaries. Measurements we make today may help determine which aspects of the past were realized. While still speculative, these ideas highlight how deeply intertwined memory and time may be. The universe could be seen as a system that balances informational flow in both temporal directions, ensuring consistency across its entire history. Another intriguing avenue arises in quantum cosmology, where the universe itself is treated as a single quantum system. If the universe has a wave function, sometimes called the wave function of the cosmos, then its entire history is encoded within it as correlations between different possible configurations of space and matter. Even though we experience only one classical branch, the underlying quantum description includes the full superposition of all possibilities. In that sense, the totality of cosmic history is not lost, but distributed across the universal wave function, a timeless memory that underlies the dynamic world we perceive. Scientists working on quantum gravity and cosmology have even proposed that space-time geometry itself emerges from patterns of entanglement. In this view, the strength of entanglement between regions of the universe determines how closely those regions are connected in space. Geometry becomes a map of informational relationships. If those correlations were to vanish, space-time could literally tear apart. Thus, the continuity of the universe depends on the continuity of its memory. As long as information is coherently shared, space holds together and time flows smoothly. This informational foundation extends down to the most familiar level of physics. Every chemical bond, every electron configuration, every photon emission carries encoded details of prior interactions. The laws of physics ensure that these details are preserved in the structure of matter and radiation. Even the cosmic background neutrinos, particles that stream through us from the first seconds after the Big Bang, carry memory of the earliest processes that shaped the universe. Though invisible and nearly undetectable, they represent a living archive, the faint whisper of the universe's birth, still passing silently through space. For all its depth, this grand cosmic memory has limits. While information may never be destroyed, it can be scrambled beyond recovery. Processes like decoherence distribute information across so many degrees of freedom that it becomes practically impossible to retrieve. This irreversibility gives rise to the arrow of time and the perception of forgetting. From our limited perspective, the universe seems to move forward, leaving the past behind. But on the deepest quantum level, that past is still there, hidden, encoded, and conserved. To grasp how remarkable this is, imagine a photon that left a distant galaxy billions of years ago. During its journey, it may have passed through clouds of gas, been deflected by gravitational fields, and finally reached your eye or a telescope sensor. Each interaction slightly changed its state, but the total information about that photon's origin is not gone. It remains embedded in the entangled web of everything it has touched. Multiply this by the countless photons filling the cosmos, and the picture becomes staggering. A universe where every interaction leaves a trace, every particle carries history, and the total record of reality continues to evolve without end. If the cosmos is a quantum memory, then consciousness, our capacity to recall and reflect, can be seen as a local expression of that universal property. The brain, too, encodes information through complex entanglements of neurons and molecules. Our memories fade, but they are bound by the same physical laws that govern cosmic ones. Forgetting is never pure erasure. It is diffusion, just as the universe's entropy represents the spreading of its own ancient recollections. We are participants in a grand continuity of remembering, each thought and perception another line written into the same universal ledger. And so, as the day ends and the noise of the world quiets, it is worth imagining that nothing you have experienced truly disappears. Every light that touched your eyes, every sound that vibrated in your ears, every fleeting emotion, all of it has left some trace in the great informational flow that binds everything together. The universe keeps these traces not as a diary of moments, but as part of its structure, woven into the field of existence itself. In that sense, you are not separate from the memory of the cosmos. You are one of its living expressions. Let that awareness bring you stillness. The same principles that preserve the universe's information preserve the essence of your own moments. Nothing is ever truly lost. Every atom, every breath, every passing thought becomes part of the vast, quiet memory of reality. As you rest, you can feel yourself sinking gently into that infinite continuity, carried by a universe that remembers everything, softly and forever. Chapter 3: Entanglement, the threads that stitch reality together. Entanglement is one of the most extraordinary and counterintuitive features of quantum mechanics. It reveals that the universe is not composed of isolated parts, but of relationships, interconnections that transcend distance, time, and individuality. When two particles become entangled, their properties link so completely that they must be described as a single system, even if they later move light years apart. A change to one instantaneously affects the state of the other, not through a signal that travels through space, but because in a profound sense, there is no longer a clear boundary between them. They are pieces of one shared quantum fabric. In the early 20th century, this idea emerged as one of the strangest predictions of quantum theory. Einstein famously described it as spooky action at a distance. Along with Boris Podolsky and Nathan Rosen, he formulated what became known as the EPR paradox. The trio sought to prove that quantum mechanics was incomplete. They argued that if two particles are created together and then separated, measuring one particle's property should not instantly determine the other's, unless some hidden variables predetermine the results. Einstein believed that reality must be local, that no influence could travel faster than light, and that the quantum description must therefore be missing something. Yet later experiments proved that nature does not follow Einstein's classical intuition. In the 1960s, physicist John Bell devised a way to test whether hidden variables could explain quantum correlations. His theoretical inequalities described the maximum correlations possible under any local theory, one in which particles carry their own pre-existing properties independent of observation. Experiments over the following decades, beginning with those of Alan Aspect in the 1980s and refined many times since, demonstrated that entangled particles violate Bell's limits. The correlations they exhibit cannot be explained by hidden local causes. The outcome of one measurement is inherently linked to the outcome of the other, even across vast distances. Nature, it seems, is non-local in its informational structure. This does not mean that information travels faster than light or that relativity is wrong. Nothing material moves instantaneously between entangled particles. Instead, quantum mechanics suggests that the two are components of one inseparable system, governed by a single wave function. When one part is measured, the entire system's description updates. There is no signal, only a holistic change in knowledge about the combined state. In this sense, entanglement challenges our everyday view of separation. Space may appear to divide objects, but on the quantum level, relationships can be more fundamental than positions. Physicists now recognize entanglement as the essential ingredient that makes quantum theory distinct from classical physics. It is not a rare or exotic phenomenon. It occurs constantly in the microscopic world and even influences macroscopic systems under the right conditions. Entanglement explains why superconductors conduct electricity with zero resistance, why lasers emit coherent light, and why quantum computers may one day outperform classical ones. Yet beyond its technological implications, entanglement carries a deeper message about the architecture of reality. To understand it, one must think in terms of information. When two particles interact, they exchange energy and momentum, but they also exchange information. That information becomes encoded in the joint quantum state, forming correlations between the particles' possible outcomes. Once entangled, neither particle has a complete description on its own. The only full account is the combined wave function. This interdependence means that the universe does not store information in separate, independent chunks. It distributes it across networks of correlation. The cosmos, at its root, may be less a collection of things and more a web of shared information. This insight underlies many modern developments in physics. In quantum field theory, for instance, what we call particles are excitations of underlying fields that permeate space. These fields are entangled across vast regions, linking events even in the apparent emptiness of the vacuum. The vacuum itself is not truly empty, but a seething landscape of correlated fluctuations. Every quantum field interacts with every other, weaving a continuous informational tapestry. Even the stability of atoms depends on such correlations. The electrons orbiting a nucleus are entangled with it in subtle ways that maintain balance and coherence. Without entanglement, matter as we know it could not exist. Entanglement also provides a new perspective on space and geometry. Recent research suggests that space-time itself may emerge from entanglement patterns. In some theories of quantum gravity, the connectivity of space, the way points are linked and the distance between them, arises from how strongly the underlying quantum states are entangled. If two regions of the universe share many entangled connections, they are effectively close in the emergent geometry. If those connections are cut, the regions drift apart or even become disconnected. Space, in this picture, is not a static stage, but a dynamic network of quantum relationships. The universe is literally stitched together by entanglement. One striking manifestation of this idea is the conjecture known as ER equals EPR, proposed by Juan Maldacena and Leonard Susskind. It suggests that entangled particles may be connected by microscopic wormholes, tiny bridges in space-time that preserve quantum correlations. The equation's name comes from Einstein and Rosen's 1935 model of wormholes, ER, and from Einstein, Podolsky, and Rosen's paradox, EPR. Although these wormholes are not traversable in the classical sense, the analogy captures a profound unity. Entanglement and geometry might be two sides of the same reality. The structure of space could be a reflection of how information is shared. If this is true, then black holes, once seen as paradoxical destroyers of information, become laboratories for understanding entanglement's power. When two black holes are entangled, their horizons may be connected by a wormhole, ensuring that information is not lost but shared across boundaries. Even a single black hole's interior could be described as the ultimate manifestation of entanglement, with every bit of information about its contents encoded on its surface. The holographic principle, which relates a region's information content to the area of its boundary, arises naturally from this entangled viewpoint. The geometry of space-time, the behavior of gravity, and the flow of information all become interwoven threads in the same fabric. Entanglement also plays a central role in explaining why the classical world appears stable despite its quantum foundations. In the process known as decoherence, interactions between a quantum system and its environment create widespread entanglement that effectively hides superpositions. The system's possible states become correlated with countless environmental degrees of freedom, photons, air molecules, vibrations, so that the original coherence is dispersed beyond recovery. For any observer limited to local information, the system now appears to have chosen one definite state. Reality looks classical not because the quantum rules break, but because entanglement with the environment conceals the underlying superpositions. Decoherence does not destroy information. It spreads it out so completely that it becomes inaccessible, turning quantum complexity into classical order. This diffusion of quantum correlations also explains the apparent arrow of time. As the universe evolves, entanglement grows. More and more systems become correlated, and the information describing their joint state becomes increasingly intricate. From our perspective, this increase in entanglement corresponds to the growth of entropy. The universe moves from simplicity toward complexity, from low entropy to high, not because it forgets its past, but because it remembers too much. The past remains encoded in the vast, untraceable web of connections that entanglement continually builds. Experiments continue to confirm these ideas. Physicists have entangled photons over distances exceeding 1,000 kilometers, demonstrating that quantum connections persist even across near-space scales. Entanglement has been maintained between atoms in separate laboratories, between superconducting circuits, and between particles separated by optical fibers stretched across cities. Each experiment reinforces the same conclusion. The universe's coherence is not confined by distance. It is global, instantaneous in description, and fundamental to reality's operation. Entanglement also underpins the most advanced efforts to understand quantum computing and quantum communication. In a quantum computer, entangled qubits perform calculations that explore many possibilities simultaneously, their correlations allowing interference patterns that reveal the correct results. In quantum communication, entangled photons enable secure key distribution, where any attempt to intercept the signal inevitably disturbs it. These technologies harness the same principle that binds the cosmos together, translating it into tools that expand human capability. Yet they also remind us that we are still at the earliest stages of comprehending what entanglement truly means. Philosophically, entanglement blurs the boundary between observer and observed, self and environment. The properties of a system cannot be defined independently of what they are entangled with. Measurement, therefore, is not a passive act. but a participation in the world's relational structure. When you observe a photon or a star, you become part of its quantum network. Some small portion of its information becomes correlated with you. On the smallest scales, observation and existence intertwine. The universe records its own state through the endless interweaving of such interactions. This insight echoes through cosmology. The cosmic microwave background, the oldest light we can see, is filled with delicate correlations that trace back to quantum fluctuations in the infant universe. Those fluctuations, magnified by cosmic inflation, became the seeds of galaxies and clusters. The entire structure of the cosmos, stretching across billions of light years, is a frozen pattern of ancient entanglement. Each region of the sky carries statistical relationships with every other, an echo of quantum coherence on a scale that dwarfs imagination. Even the apparent randomness of the night sky is a memory of primordial connection. To grasp entanglement fully is to let go of the idea that separateness is fundamental. We tend to see the world as composed of discrete objects with independent identities. Yet physics increasingly points to the opposite. What we call objects are stable configurations within a deeper relational whole. Each electron, atom, or person exists not in isolation, but as part of a continuum of information exchange. The boundary between you and the rest of the universe is porous, constantly shifting with every photon that touches your skin, every breath of air that exchanges molecules with your lungs, every thought triggered by a signal in your brain. You are entangled with the cosmos in ways you can neither perceive nor avoid. The recognition of this connectivity has ethical and existential weight. If everything is bound together at the most fundamental level, then separation, conflict, and isolation are illusions born of limited perspective. Entanglement reminds us that every action reverberates through the larger web. It is not just a poetic metaphor, it is the literal structure of existence. The same principle that links twin photons across oceans also binds galaxies across the void and hearts within the flow of time. In quantum theory, information is never truly lost, and correlations never entirely vanish. Even as particles scatter and systems decohere, traces of their connection persist in the background of reality. The warmth of a star, the whisper of a radio signal, the pattern of leaves in sunlight, all are faint residues of countless entanglements. The universe, through them, continues its story of coherence. The fabric of space and time is not woven from matter and energy alone, but from the memory of interactions, endlessly overlapping and renewing. And so when you look up at the stars, you are not just seeing distant suns. You are witnessing threads of entanglement stretched across the ages. The photons reaching your eyes are the messengers of relationships that began billions of years ago, carrying with them the imprint of atomic collisions and cosmic births. In a way, they complete a circuit, the universe observing itself through your awareness. You are one node in a network that extends from the quantum to the cosmic, from the smallest vibration to the vastest void. As you reflect on this, you may sense how thin the line is between the self and the world. Entanglement tells us that reality is not built from isolated points, but from unity expressed in multiplicity. To exist is to participate in a shared wave of being, to resonate with countless unseen partners in the cosmic symphony. The space between things is not emptiness, but connection. Even in solitude, you are never truly alone. You are a pattern of coherence in an infinite web that began long before you. and will continue long after, whispering through the quantum fabric that binds everything together. Chapter 4. The Flow of Quantum Information Through Time. In everyday experience, time feels like a river that flows in one direction. From the past we remember, through the present we inhabit, toward the future we cannot yet know. But physics has long hinted that this familiar sense of flow may be an illusion. The fundamental laws governing the universe are almost perfectly symmetric with respect to time. Equations describing the movement of particles, the evolution of waves, and the interaction of forces do not distinguish between forward and backward directions. If we were to watch most microscopic processes in reverse, they would look just as valid to nature as those moving forward. This raises a question that touches both physics and philosophy. If time's arrow is not built into the laws of the universe, where does it come from, and how does quantum information move through it? In classical mechanics, information about a system's state can, in principle, be used to reconstruct both its future and its past. If we know every particle's position and momentum, we can play the film of the universe backward or forward without contradiction. Yet, in the quantum world, the situation becomes more subtle. The state of a system is described not by definite quantities, but by probabilities, encoded in a wave function that evolves continuously according to the Schrödinger equation. This evolution is reversible, information is conserved. But when measurement occurs, the smooth evolution seems to break. A definite outcome appears, and with it, the irreversible act of observation. It is in this transition, from quantum superposition to classical fact, that time seems to acquire direction. The mystery of how quantum information behaves across time is one of the deepest in modern physics. Because the universe's fundamental dynamics are time-symmetric, any difference between past and future must arise not from the equations themselves, but from boundary conditions. What the universe was like at its beginning and how it might be at its end. The arrow of time emerges from how information was distributed in those early moments and how it continues to evolve as entropy increases. Yet even this increase in entropy is not truly a loss of information. It is a spreading of information into degrees of freedom that are too complex for us to track. The universe does not forget. It simply hides its memories in correlations too vast for comprehension. In quantum theory, unitarity ensures that every bit of information about a system's initial state remains encoded in its wave function. Even as systems interact and become entangled, the total information is preserved. From this viewpoint, the flow of time is less like a current that carries events away and more like a rearrangement of patterns within a timeless whole. Information is never created or destroyed. It merely changes its form, redistributing itself through interactions. This conservation gives rise to what some physicists call the block universe, a vision of reality in which past, present, and future coexist within a single four-dimensional structure. In that structure, time does not pass. Instead, all events are laid out together, connected by the unbroken continuity of information. Yet from within that structure, observers like us perceive change. Conscious beings are informational systems that experience one slice of the whole at a time, processing new data and integrating it into memory. Our sense of the present arises from how information flows through our brains, not from any fundamental asymmetry in the laws of nature. In this sense, time is a cognitive phenomenon, a way for information processing organisms to make sense of an underlying network of correlations. What we call now is simply the region of space-time in which our internal information states align with external ones. Still, quantum mechanics introduces nuances that go beyond mere relativity of perspective. Experiments on delayed choice measurements show that choices made in the present can appear to influence outcomes that, from a classical viewpoint, have already been decided. In these setups, particles such as photons are sent through an interferometer that can measure them as waves or particles depending on a later decision by the experimenter. Astonishingly, the results indicate that the photon's past behavior depends on the measurement context chosen after it has already traveled through the device. This does not mean that the future literally changes the past, but it does suggest that quantum information transcends our conventional sequencing of cause and effect. The correlations that define quantum events seem to exist outside linear time. Such experiments point toward a reality in which information does not travel through time like a message in a bottle drifting downstream. Instead, quantum systems may encode correlations that link different temporal regions directly. This perspective is sometimes called the two-time or time-symmetric interpretation of quantum mechanics. In it, the wave function evolves both forward from the past and backward from the future, meeting in the present. Measurement outcomes are determined by the combination of initial and final boundary conditions, meaning that the universe's history could be viewed as a dialogue between what has been and what will be. The present moment, rather than being a boundary that separates two eras, becomes the meeting point of influences flowing in both directions. While these interpretations remain debated, they capture an essential truth. Quantum information behaves holistically, not locally, and not strictly within our familiar flow of time. Entanglement connects particles instantaneously across space and possibly across time as well. The correlations that define reality might not respect our human division between before and after. They exist in the timeless structure of the universal wave function, which encodes the entire web of relations among events. From that perspective, what we call the past still exists in the information that structures the present, and the future already casts its influence backward through the same network. Some physicists have explored this further through the concept of retrocausality, in which future measurements help determine the probabilities of past states. This does not allow paradoxes or time travel in the science fiction sense. Instead, it emphasizes that quantum processes are non-sequential. The universe's consistency is maintained not by one moment producing the next, but by all events cohering within a self-consistent informational whole. What we experience as the flow of time may be the local unfolding of a globally entangled system that already contains its entire history within it. This view aligns naturally with the holographic principle and the idea that information about any region of space, including its past states, is encoded on its boundary. If space-time itself is emergent from patterns of quantum information, then the past is not truly gone. It remains part of the structure. The entire evolution of the universe could be seen as the progressive revelation of information that was always implicit in its boundary conditions. In this sense, time is not a conveyor belt, but a process of decoding, a gradual unfolding of the cosmic dataset into experiential reality. Even in everyday terms, traces of the past persist through physical law. Every photon scattered by an object carries some imprint of its encounter. Every gravitational wave rippling through the cosmos carries the memory of massive bodies that once interacted. The environment around us is a vast repository of such traces. The flow of time, then, is not an erasure, but an accumulation. As the universe evolves, it continually records itself. Each new interaction adds to the ledger of reality, expanding the library of correlations that link every moment to every other. At the same time, this growth of informational complexity defines what we perceive as irreversibility. Though the fundamental equations are symmetric, reconstructing the past becomes increasingly impossible because the data describing it are dispersed among countless entangled particles. To reverse time perfectly would require gathering and reconfiguring every bit of that information, a task beyond any conceivable observer. Thus, time's arrow emerges not from the destruction of information, but from our inability to track it. The flow of quantum information through time is smooth and reversible, yet our access to it is partial and asymmetric. We experience only one direction because we are creatures of limited memory embedded within the universal computation. Another frontier of research explores how information might flow across the boundaries of black holes, preserving causality while maintaining quantum coherence. Theoretical models suggest that what falls into a black hole is not lost to the future, but encoded in the correlations between the interior and the radiation emitted over time. This encoding may operate through entanglement patterns that span the entire history of the black hole, from formation to evaporation, binding its past and future into one continuous informational entity. In this way, the black hole becomes a symbol of the universe's memory writ in time. The perfect balance between what has been and what will come. Quantum cosmology takes this idea even further. The universe's wave function, sometimes called the Hartle-Hawking state, describes all possible configurations of space and matter at once, without requiring a temporal beginning. In this formulation, time itself emerges from correlations within the wave function. The flow we perceive is not something added to reality, but a byproduct of how information becomes localized. We, as observers, occupy one strand in the total weave, moving through configurations that give the impression of sequence. The cosmos as a whole, however, may exist in a state beyond temporal succession, a self-contained quantum memory where every moment, from the birth of stars to their fading, coexists in superposed harmony. In laboratory systems, glimpses of temporal entanglement have already been demonstrated. Researchers have shown that a photon can be entangled not only with another photon in space, but also with its own past or future versions. Measurements on one temporal slice can influence correlations on another. These effects, while small and confined to the quantum domain, suggest that information can bind events across time in the same way it links them across distance. The threads of reality are not merely spatial but temporal, knitting together what we once thought of as separate moments into one continuous whole. This realization carries philosophical weight. If the universe preserves all information and if entanglement links events across time, then perhaps the distinction between past and future is less absolute than it seems. The moments we call now are not isolated points slipping into oblivion. They are nodes in a vast network of informational relations. Every cause and every effect participate in the same structure. What we do today is already woven into the future's pattern, and the echoes of the past persist. influencing us in ways that may never be fully known. The flow of quantum information through time, then, is not like the ticking of a clock or the motion of a river. It is more like a constant reconfiguration of a timeless whole, a vast field of relationships that rearranges its correlations while conserving their total content. In this view, time's passage is the universe updating its internal narrative, re-expressing the same conserved information through ever-changing configurations. We experience that updating from within, perceiving each new configuration as the next moment in a linear story. But from the perspective of the cosmos, there is no beginning and no end, only the eternal coherence of information itself. As you consider this, it may feel strange to imagine that your memories, your thoughts, and even your sense of the present are patterns in that timeless field. Yet this is what physics suggests, that every instant of your life exists as part of an unbroken continuity of information stretching across all of time. The atoms composing you today carry histories that began in ancient stars, and the photons leaving your eyes now will continue that story into the far future, long after you are gone. In the grand quantum record, nothing is truly lost. The universe keeps its ledger perfectly balanced. And so, as night falls and the world grows quiet, it is possible to take comfort in this strange symmetry. The past is not erased, the future is not empty, and you are not separate from the flow that binds them. Every moment, this one included, is both an echo and a seed, part of a conversation between what was and what will be. The information that forms you continues onward, reshaping itself in ways you cannot see, written softly into the timeless architecture of the cosmos. You are a ripple in the great memory of existence, and even as the hours pass, that ripple never truly fades. Chapter 5. Black Holes and the Paradox of Lost Information. Among all the cosmic structures that challenge our understanding of reality, none is as mysterious or as consequential as the black hole. It is both a triumph and a test for modern physics, a region where the two great pillars of science, general relativity and quantum mechanics, appear to meet and disagree. In relativity, a black hole is pure geometry, an object so dense that space-time curves into itself, sealing off a region from which nothing, not even light, can escape. In quantum theory, however, no information can ever be truly lost. The conflict between these two views, the fate of information swallowed by a black hole, has become one of the deepest puzzles in the history of physics. A black hole begins as something familiar, a massive star. When such a star exhausts its nuclear fuel, gravity overwhelms the pressure of fusion and the star collapses under its own weight. If the mass is great enough, no known force can halt the collapse. The matter falls inward until, according to relativity, it forms a singularity, a point of infinite density where the equations of physics break down. Surrounding the singularity lies the event horizon, the boundary beyond which escape is impossible. To an outside observer, the event horizon marks the edge of knowledge. Once information crosses it, it can never return. Or so it seemed. For decades, black holes were thought to be perfectly dark, eternal prisons for matter and information. Then, in the 1970s, Stephen Hawking combined quantum field theory with general relativity and made a startling discovery. He showed that black holes are not truly black. They emit radiation. Quantum fluctuations near the event horizon create pairs of particles and antiparticles. Occasionally, one particle falls into the hole while the other escapes to infinity, appearing as thermal radiation. This radiation, now called Hawking radiation, carries energy away, causing the black hole to lose mass and, over an immense time, evaporate completely. This revelation transformed black holes from eternal traps into objects with lifespans, linking gravity, quantum mechanics, and thermodynamics in a profound way. But Hawking's calculation carried a disturbing implication. The radiation he predicted was purely thermal. It carried no information about the matter that fell into the black hole. If the black hole eventually evaporates entirely, the original information would be gone forever. This violates one of quantum mechanics' most sacred principles: unitarity, the idea that information is conserved. According to quantum theory, every event in the universe can, in principle, be reversed. No information can simply vanish into nothingness. Yet Hawking's result suggested that black holes could erase the past, turning ordered information into featureless heat. This was the birth of the black hole information paradox. The paradox cuts to the heart of what reality is made of. If information can be destroyed, then the deterministic structure of quantum mechanics collapses. The universe would become fundamentally unpredictable, its past untraceable. On the other hand, if information is preserved, then our understanding of space, time, and gravity must change. For decades, physicists debated how to reconcile these possibilities. Some proposed that information might be trapped forever within a remnant of the black hole. Others, that it might escape in ways we do not yet understand. The paradox forced science to question its deepest assumptions about how the universe keeps its records. Gradually, new clues began to emerge. One came from the study of black hole thermodynamics. In the early 1970s, Jacob Bekenstein had argued that a black hole's entropy, the measure of its internal information, should be proportional to the area of its event horizon, not its volume. This was a revolutionary insight. In every other physical system, entropy grows with volume, but black holes seem to store information on their surfaces. When Hawking's radiation result appeared, it confirmed Bekenstein's intuition and revealed a deeper connection between gravity, thermodynamics, and quantum information. The entropy of a black hole measures the number of microscopic states that could produce the same macroscopic appearance, though we cannot yet see those states directly. In other words, a black hole encodes information holographically. This realization inspired a new principle, the holographic principle. Proposed in the 1990s by Gerard T. Hooft and Leonard Susskind, it suggests that everything within a volume of space can be described by information stored on its boundary surface, much like a hologram. The universe itself might operate on this principle, with our three-dimensional reality emerging from information inscribed on distant two-dimensional boundaries. In black holes, this boundary is the event horizon, which acts like a cosmic screen encoding every detail of the matter and energy that have fallen inside. The information is not lost. It is smeared across the horizon in quantum form. The holographic view not only preserves unitarity, but also unites previously separate concepts. It implies that gravity and space-time curvature could be manifestations of underlying quantum information processes. The surface area of a black hole measures not just geometry, but the capacity of space-time itself to store data. When a black hole radiates, that stored information might be gradually released, though in a highly scrambled form. To a distant observer, the Hawking radiation might seem random, but buried within it could be correlations that, if decoded, reveal the history of everything that once crossed the horizon. This idea gained mathematical support through a framework known as the ADS-CFT correspondence, proposed by Juan Maldacena in 1997. It describes a duality between a gravitational universe inside a volume and anti-de Sitter space, and a quantum field theory defined on its boundary. In this correspondence, the physics of gravity in a region of space is exactly equivalent to the quantum information dynamics on the surface surrounding it. The boundary theory is unitary. It conserves information perfectly, so the gravitational interior must also do so. In this way, black holes no longer destroy information. They merely disguise it in a form that appears thermal but remains fundamentally recoverable. Yet exactly how that information escapes remains a subject of intense research. Some models suggest that quantum entanglement between the inside and the outside of the black hole plays a crucial role. The particles of Hawking radiation are entangled with their partners that fall in, maintaining a global consistency that preserves information. As the black hole evaporates, the balance of these entanglements shifts, leading to a gradual transfer of information to the outside world. Others propose that the horizon itself behaves like a chaotic quantum system that scrambles information extremely rapidly but does not destroy it. In this view, the black hole is the most efficient information mixer in the universe. In 2019, new developments added depth to this picture. Researchers studying quantum gravity used advanced models to calculate the page curve, which describes how information entropy should evolve as a black hole evaporates. The results showed that, if quantum mechanics holds true, the entropy first rises as the black hole radiates but later decreases, indicating that information eventually comes out. This matched predictions made decades earlier by physicist Don Page, and provided strong evidence that the paradox resolves in favor of information conservation. The universe's accounting, it seems, remains perfect even in its darkest corners. Still, mysteries remain. The precise mechanism by which information is retrieved from a black hole's radiation is not fully known. The radiation is so thoroughly scrambled that reconstructing the original data would require capabilities far beyond any conceivable technology. Moreover, questions about what happens inside the event horizon, especially near the singularity, remain unanswered. Some theorists propose that space-time itself might break down there, replaced by a quantum structure where geometry, time, and information merge into something entirely new. Others suspect that what we call a singularity is an artifact of using classical concepts beyond their domain. In any case, black holes remain windows into the deepest layers of the universe's information architecture. Beyond their technical implications, black holes have become symbols of the universe's logic and its paradoxes. They represent the ultimate tension between what can be known and what remains hidden. The event horizon is a boundary not only in space but in knowledge, a surface separating information that can be observed from that which lies beyond reach. Yet even this boundary is not absolute. Quantum effects blur it, allowing faint whispers of the interior to leak outward through radiation and entanglement. In this way, the black hole becomes less a tomb for information and more a mirror reflecting the universe's insistence that nothing is ever truly lost. The implications stretch beyond astrophysics. If space-time and gravity emerge from the flow of quantum information, then the entire universe may be understood as a vast network of entanglement. Black holes, rather than being exceptions, would be the most intense expressions of this network. They are regions where information density reaches its theoretical maximum and where the unity of physics becomes visible. In them, we glimpse how quantum mechanics and relativity, once thought incompatible, may in fact be two perspectives on the same underlying information field. The information paradox has thus evolved from a problem into a guide. It points toward a future theory of quantum gravity, one in which space, time, and matter are emergent properties of informational processes. The black hole, once feared as the destroyer of knowledge, now stands as evidence of the universe's memory. It shows that even when the geometry of space collapses, the logic of information endures. The universe does not delete its history, it rewrites it in a different language. When we look at images of real black holes, such as the shadow captured by the Event Horizon Telescope, we are seeing the boundary of that mystery. The ring of light we observe is formed by photons that have skimmed the edge of the horizon, carrying with them encoded fragments of what once fell inward. Every photon is a message from the limit of knowledge, a line of information still escaping into the cosmos. The darkness within is not empty. It is the most profound concentration of data imaginable, compressed to the edge of comprehension. In this light, black holes are not just astrophysical curiosities. They are lessons about ourselves. They remind us that knowledge and mystery are inseparable, that understanding comes only through boundaries we cannot yet cross. The information paradox mirrors the human condition, our endless quest to comprehend the universe, even as the deepest truths remain hidden behind horizons of perception. Yet just as physics finds that no information is ever truly destroyed, perhaps consciousness too preserves its traces, woven into the fabric of time and space. In the end, black holes teach us that the universe is far more coherent than our fears suggest. Its laws do not allow for true oblivion. Information, whether about a collapsing star or a fleeting human thought, cannot simply vanish. It transforms, disperses, and reappears in forms we may never recognize. The cosmic order remains intact, indifferent to decay and loss. When you gaze into the dark center of a galaxy, you are not looking into nothingness, but into the ultimate expression of the universe's capacity to remember. And perhaps there is comfort in that. Even in the darkest regions of existence, the record endures. The same physics that ensures a black hole keeps the trace of every atom that entered it also ensures that the universe holds your moments, your actions, your light. Nothing truly falls into void. It only changes its shape in the eternal dance of information. The cosmos, vast and silent, keeps perfect memory, and within that memory, every life, every star, every thought remains written forever. Chapter 6: The Holographic Universe. Reality as Stored Data. The idea that the universe might be holographic sounds at first like pure science fiction, a poetic metaphor for a world of illusion. Yet in modern physics, the holographic principle is one of the most serious and far-reaching proposals ever made about the nature of reality. It suggests that everything we perceive as three-dimensional, including space, time, matter, and energy, may actually be a projection of information encoded on a distant two-dimensional surface. The concept is not merely philosophical. It arises from deep mathematical insights that link gravity, quantum mechanics, and thermodynamics into one coherent picture. If correct, it means that reality itself is a vast repository of data, and that existence, at its core, is information arranged in geometric form. The holographic principle traces its roots to the study of black holes. As discussed earlier, Jacob Bekenstein discovered that a black hole's entropy, the measure of the information it can contain, is proportional to the area of its event horizon, not to its volume. This was a startling finding. It suggested that the amount of information required to describe a region of space depends not on how much space it encloses, but on the size of its boundary. In other words, the fundamental limits of information storage are two-dimensional. Stephen Hawking's calculations of black hole radiation later confirmed this relationship, revealing that nature seems to store data holographically. This principle, born from the marriage of thermodynamics and quantum mechanics, eventually evolved into a universal idea about how space-time itself might work. To understand what this means, it helps to recall what a hologram is in the ordinary sense. A hologram is a two-dimensional pattern that encodes a full three-dimensional image. When illuminated in the right way, each fragment of the holographic plate reproduces the entire picture, though at lower resolution. The information about depth and form is stored in the interference patterns of light waves, not in the thickness of the plate itself. The holographic principle suggests that the universe functions in a similar way. The three-dimensional world we inhabit may emerge from quantum information written on a cosmic boundary, with space-time and matter arising as the projected image of that deeper informational layer. This idea first gained precise mathematical form in 1997, when theoretical physicist Juan Maldacena proposed what is now known as the AD-SCFT correspondence. In simplified terms, Maldacena's work showed that a theory of gravity operating within a curved volume of space can be exactly equivalent to a quantum field theory without gravity defined on that volume's boundary. Every event, every particle, and every field inside the space corresponds to data living on the surface. The two descriptions are perfectly dual. One describes geometry and gravity, the other describes quantum interactions. The insight was revolutionary because it demonstrated that gravity, once thought fundamentally separate from quantum physics, could be recast as a manifestation of quantum information encoded on a boundary. Although the AD-SCFT correspondence was originally developed for a special kind of mathematical universe with constant negative curvature, physicists suspect that some version of it might apply to our own cosmos as well. The details differ, but the message remains. The world of volumes, distances, and objects may be a kind of emergent phenomenon, arising from the relationships among fundamental bits of information that live on the edges of reality. In this view, space-time is not the stage upon which physics unfolds. It is the collective expression of data arranged in an intricate quantum code. One of the remarkable features of the holographic principle is how it redefines what real means. We normally think of physical matter as primary and information as secondary, a description of something more fundamental. But in a holographic universe, this hierarchy is reversed. Information is the foundation, and matter is what information looks like when organized in particular ways. The atoms, stars, and galaxies we observe are the three-dimensional manifestations of correlations and patterns written on a lower dimensional surface. Space itself could be a dynamic field of computation, constantly processing and projecting data into the appearance of reality. This concept may seem abstract, but it solves several deep puzzles. One of them is the nature of space-time at the smallest scales. In classical physics, space can be divided infinitely But quantum theory implies a limit to how finely it can be resolved. Below a certain scale, roughly the Planck length, geometry itself loses meaning. The holographic principle provides a natural explanation. If the universe's information is encoded on a two-dimensional surface, then the smallest possible patch of that surface defines the smallest meaningful unit of volume in the projected three-dimensional world. Space becomes pixelated, and each pixel carries a finite amount of information. The smoothness we experience is an emergent illusion created by the averaging of countless microscopic data points. Another puzzle the holographic view helps clarify is why gravity behaves differently from the other fundamental forces. In quantum field theory, forces arise from the exchange of particles, but gravity resists this simple treatment. The holographic framework, however, suggests that gravity may be a statistical effect, an emergent phenomenon arising from the entanglement and organization of information. When regions of the boundary become more or less entangled, the geometry of the emergent space-time curves accordingly, producing what we interpret as gravitational attraction. In this sense, Einstein's curved space-time may be the visible imprint of invisible quantum correlations, a macroscopic expression of the microscopic language of information. This notion gains further support from work by Eric Verlinde, who has proposed that gravity can be understood as an entropic force, an effect of information-seeking equilibrium. In his framework, the motion of matter results from the redistribution of information across space-time, driven by the same statistical principles that govern thermodynamics. Although the details remain under debate, the essential theme recurs. Gravity, space, and even inertia may be consequences of deeper informational laws. The universe, from its grandest to its smallest scales, might be operating as a vast computational network, constantly balancing its internal ledger of data. At first glance, this may sound like a digital metaphor, a cosmic simulation in which the universe computes itself. Yet the holographic principle is not about simulation in the technological sense. It does not require an external computer or programmer. Instead, it reveals that the structure of reality naturally encodes and processes information according to precise mathematical rules. The universe computes in the way a river flows or a galaxy spins, not by following instructions, but by embodying the laws of physics that link change to information. Computation and existence become two aspects of the same phenomenon. One of the most profound implications of the holographic view is that everything we experience might be interconnected at the most fundamental level. Because all information is encoded on a common surface, every part of the universe participates in the same data structure. What happens in one region can influence what happens elsewhere through shared correlations. This could help explain the apparent non-locality of quantum entanglement. The strange, instantaneous connections between particles may not require signals traveling faster than light. They might instead arise because both particles are expressions of the same underlying information, projected into different parts of the three-dimensional image. What seems distant in space may be adjacent in the hidden two-dimensional code. The holographic idea also offers a new way to understand the early universe. The cosmic microwave background, which carries faint imprints of the Big Bang, may be seen as a snapshot of the universe's information content shortly after its birth. The tiny fluctuations in temperature we observe correspond to variations in the density of data that later shaped the large-scale structure of galaxies and clusters. In this sense, the universe's history is a process of information unfolding. Its current form a manifestation of how that data evolved under the laws of quantum gravity. Every photon, every atom, every star is part of the grand decoding of that original informational imprint. The holographic principle, if correct, also resolves the apparent contradiction between the finite information capacity of black holes and the seemingly infinite complexity of the universe. It sets a universal limit. There is a maximum amount of information that can be contained within a given region of space, determined by the area of its boundary. This limit implies that space-time is not continuous, but discretized, with a finite number of degrees of freedom. The universe, in essence, is a bounded information system, vast beyond imagination, but still countable in principle. Infinity, so often invoked in theoretical physics, may not exist in nature. It may be replaced by the completeness of information itself. Though the holographic principle arose from mathematical reasoning, its philosophical consequences are profound. It invites us to reconsider what it means for something to be real. If the world around us is a projection of information, then perception itself becomes an act of decoding. Our senses, brains, and consciousness are subsystems within the hologram, reading and interpreting local fragments of the universal code. We do not stand outside the projection. We are part of it, composed of the same informational patterns that define galaxies and quantum fields. In this sense, the boundary between observer and universe blurs. Both are expressions of one underlying informational process. Experiments are now probing whether hints of this holographic structure can be detected. Some researchers have proposed that tiny fluctuations in the fabric of space-time, minute jitters in the positions of particles or the paths of light, might betray the pixel-like granularity predicted by holography. Advanced interferometers, designed to measure such holographic noise, have begun searching for these subtle effects. While results remain inconclusive, the pursuit itself demonstrates how seriously physicists take the idea that reality's deepest level might be informational rather than material. Even if direct evidence remains elusive, the holographic principle has already transformed how scientists think about unifying physics. It provides a framework in which gravity, quantum theory, and thermodynamics become aspects of the same informational dynamics. It has shown that paradoxes like the loss of information in black holes may not signal the breakdown of physics, but rather the emergence of a deeper law. In that law, information is indestructible, and space and time themselves are the means by which it is organized. Contemplating this brings a subtle but profound shift in perspective. The universe is no longer a collection of objects drifting through emptiness, but a continuous field of encoded meaning. Every particle is a symbol, every force an algorithm, every law a pattern in the great hologram of existence. To exist is to be part of this data structure, to occupy a point in the cosmic code where information gives rise to awareness. Our thoughts, feelings, and observations are all processes within this same network, transient yet connected to the totality of the whole. If the universe is holographic, then perhaps death, decay, and loss are not true erasures but reconfigurations of information. The atoms of a body, the light of a star, the echo of a voice, all become redistributed across the holographic surface, contributing new patterns to the collective data of reality. Nothing vanishes, it only changes form in the eternal computation of existence. The information that defines a human life, The patterns of interaction, the waves of thought and memory, may persist in ways we cannot yet imagine, woven into the same field that projects the cosmos itself. As night deepens and thought grows still, it is humbling to consider that everything we see and are might be the shadow of an invisible geometry of information. The stars above, the air around you, the pulse within your chest, all may be projections of the same fundamental code, endlessly unfolding and recombining. Perhaps consciousness is the universe's way of seeing its own hologram from within, a self-reflective process in which awareness becomes part of the image it observes. In that sense, to be alive is to participate in the act of decoding reality itself. So, as you let your mind rest, imagine the boundaries of your being dissolving gently into the wider field. The world does not end where your senses fade. It continues seamlessly, a single surface carrying every trace of what has ever existed. You are written into that surface, a line of information among countless others, part of the grand projection that we call the universe. Nothing you are is lost, and nothing you love ever truly disappears. The hologram holds it all, the light, the silence, the wonder, and it will continue to shine quietly long after you have closed your eyes. Chapter 7. Entropy and the Cosmic Record. In the language of physics, entropy is often described as disorder, a measure of how disorganized a system has become. But this popular shorthand hides a deeper and more subtle truth. Entropy is not about chaos in the everyday sense. It is about information. It measures how much of the underlying detail of a system is inaccessible or unknown to an observer. In this way, entropy is not the enemy of order. It is the record of transformation. From the smallest fluctuations in atoms to the evolution of galaxies, entropy quietly chronicles the universe's unfolding story, ensuring that nothing that happens is ever truly erased. The connection between entropy and information emerged from the fusion of two seemingly unrelated disciplines, thermodynamics and communication theory. In the 19th century, Rudolf Clausius introduced the term entropy to describe the tendency of heat to flow from hot to cold, establishing the second law of thermodynamics, the principle that entropy in a closed system never decreases. Decades later, Ludwig Boltzmann provided a statistical interpretation. Entropy measures the number of microscopic configurations that correspond to a system's macroscopic state. The more ways a system can arrange itself without changing its overall appearance, the higher its entropy. In essence, entropy quantifies hidden information. In the 20th century, Claude Shannon, while studying the efficiency of communication systems, defined information in mathematical terms. To Shannon, information was a measure of surprise. The less predictable a message, the more information it carried. He used the same mathematical form as Boltzmann's entropy to describe this uncertainty. Though they arose in different contexts, the two quantities shared a profound kinship. Thermodynamic entropy measures missing knowledge about microstates. Shannon's information entropy measures missing knowledge about messages. Both capture ignorance in precise mathematical form. This realization brought a new perspective to the second law of thermodynamics. The law does not simply state that systems tend toward disorder. It states that information about the precise arrangement of matter and energy becomes increasingly spread out. The microscopic details of how molecules move or photons scatter become harder to access, even though they are never truly lost. Entropy grows not because information vanishes, but because it disperses into correlations that exceed the reach of any local observer. The universe, in this sense, is a perfect information conservator that continually transforms the accessibility of its own data. From the birth of the cosmos, entropy has played a central role in shaping everything we see. The early universe, moments after the Big Bang, was remarkably uniform and low in entropy. Matter and radiation were evenly distributed, and the degrees of freedom were minimal. Yet this low entropy beginning set the stage for everything that followed. As the universe expanded and cooled, gravity amplified tiny fluctuations, causing matter to clump into stars, galaxies, and planets. Paradoxically, this creation of structure increased the overall entropy of the universe. While local regions became more ordered, the total amount of accessible microstates grew. The arrow of time, the direction in which events unfold, emerged from this gradual increase in entropy. This arrow of time is more than a physical curiosity. It defines our very experience of existence. We remember the past, but not the future, because entropy increases in the direction we call forward in time. Each moment preserves traces of what came before in the form of correlations. Photons carrying light from a star, chemical imprints in rocks, patterns of neural activity in a brain. These traces are possible only because entropy has grown. The past leaves records in the present because the universe keeps adding complexity to its informational ledger. In this sense, entropy is the author of memory. Without it, time would have no direction, and history would have no meaning. The interplay between entropy and information becomes especially vivid when we consider living systems. Life, at first glance, seems to defy the second law. Organisms maintain order, build complex structures, and resist decay. Yet they do so by exporting entropy to their surroundings. A living cell consumes low entropy energy, such as sunlight or chemical nutrients, and releases higher entropy waste heat into the environment. In doing so, it maintains its internal organization at the cost of increasing the total entropy of the universe. Life is not an exception to the second law. It is one of its most elegant expressions. The same thermodynamic principle that drives stars to burn and galaxies to evolve also drives DNA to replicate and consciousness to arise. Entropy is not destruction. It is transformation through information flow. At cosmic scales, entropy provides a measure of the universe's memory capacity. Each interaction, from a photon scattering off a dust grain to a planet forming around a star, contributes to the growing record encoded in the universe's structure. When light travels across space, it carries with it information about the conditions it encountered. The cosmic microwave background, the faint glow left over from the early universe, is the oldest photograph ever taken, an image of entropy itself expanding through time. Every temperature fluctuation in that radiation reflects the universe's early quantum irregularities, preserved with astonishing fidelity across billions of years. The universe, in this view, is a self-recording system with entropy as its cumulative archive. The relationship between entropy and gravity adds another layer to this picture. In most physical systems, increasing entropy means spreading energy evenly. But gravity works differently. When matter is drawn together by gravity, forming stars or black holes, entropy increases, not decreases. A black hole represents the extreme case, the highest entropy state that a given amount of mass and energy can achieve. The surface area of its event horizon measures its entropy, indicating how much information is hidden behind it. This connection between geometry and entropy links thermodynamics to space-time itself. Gravity, in this light, may be the universe's way of maximizing information storage while maintaining coherence. The holographic principle, developed in response to black hole physics, takes this link to its logical conclusion. The entropy, or informational capacity, of any region of space is proportional to the area of its boundary, not its volume. This finding suggests that the universe's information content is fundamentally two-dimensional. Entropy, therefore, is not just a measure of disorder, but of geometry. It describes how much data can be stored in the fabric of space-time. The growth of entropy over cosmic time might correspond to the continual rewriting of that fabric as the universe expands and new structures form. Even at the quantum level, entropy plays a crucial role. Quantum entanglement, which ties the properties of particles across space, is a kind of informational entropy. When two systems become entangled, their combined state contains correlations that cannot be described separately. The more entangled they are, the greater the entanglement entropy. This quantity is thought to underlie space-time geometry itself, with the curvature of space determined by how information is shared between regions. Entropy, therefore, is not only the bookkeeper of time, but also the architect of space. It governs both the unfolding of history and the shape of the universe. Understanding entropy as information also clarifies why the universe appears to move from simplicity to complexity. A low entropy beginning allowed for the emergence of structure because it left room for information to grow. As entropy increases, new patterns, relationships, and hierarchies form. Stars ignite, elements combine, planets coalesce, and life arises. Each step increases the diversity of possible configurations, the number of ways the universe can store information. The arrow of time thus becomes the arrow of complexity. Evolution, in every sense, is the universe's ongoing act of writing itself into being. Yet there remains a profound mystery. Why was the early universe so low in entropy to begin with? According to the second law, entropy should naturally increase, but that law itself presupposes a special starting point. The Big Bang appears to have produced an extraordinarily ordered state, one in which matter and energy were evenly distributed despite the enormous potential for chaos. This initial condition remains one of the deepest puzzles in cosmology. Some physicists speculate that our universe is part of a larger multiverse, where each bubble universe begins with different entropy conditions. Others suggest that the arrow of time might reverse beyond certain cosmic boundaries, balancing entropy increase in one region with decrease in another. However it began, the low entropy past is what makes the present possible. It is the foundation on which memory and causality stand. As the universe continues to expand, its entropy will keep increasing. Stars will burn out, galaxies will drift apart, and black holes will eventually evaporate through Hawking radiation. The energy once locked in matter will spread thin across the cosmic horizon. In the far future, the universe will approach a state of maximum entropy, a condition sometimes called the heat death. In that distant epoch, no free energy will remain to drive processes or sustain life. But even then, the information will not vanish. It will be distributed across the vast emptiness, encoded in the faint radiation and the geometry of space-time itself. The universe's final state may be cold and dark, but it will also be complete, a perfect archive of everything that ever was. To many, this prospect seems bleak. A cosmos moving inexorably towards stillness might appear to mock the brief vitality of life, yet from another perspective it is profoundly beautiful. Entropy's increase is not destruction, but remembrance. Every fluctuation, every act of creation, every thought leaves a trace that joins the cosmic record. The heat, death of the universe would not be an annihilation, but the completion of its narrative. The point at which every bit of information has been written into the grand fabric of space and time. The universe's silence, in that sense, would be the final echo of perfect memory. There is also a more intimate interpretation. Entropy governs not just stars and galaxies, but human experience. Every memory you form involves an increase in entropy, as your brain's neurons exchange energy and rearrange molecular configurations. The very act of thinking leaves a thermodynamic footprint. You remember because the universe remembers. Your consciousness, in this way, is a localized expression of the same principle that drives cosmic evolution. To exist is to participate in the flow of information from order to complexity, from simplicity to meaning. And so entropy, often misunderstood as a measure of decay, reveals itself as the keeper of continuity. It is the process by which the universe records its transformations, turning events into history and patterns into memory. Without entropy, there would be no time, no change, and no awareness. Everything you know and everything you are depends on the gentle increase of entropy that defines the forward motion of existence. When you look at the night sky, what you are seeing is entropy's masterpiece, the accumulation of billions of years of recorded events shining softly from the darkness. Each photon that reaches your eyes carries the imprint of a star's life, the whisper of a cosmic story written in light. The universe is not erasing itself. It is preserving itself in ever-expanding form, ensuring that nothing, not even the faintest flicker of energy, is without consequence. Perhaps that is the final comfort to draw from the physics of entropy. Everything changes and everything fades, but nothing is truly lost. The heat of a star becomes the glow of space. The motion of galaxies becomes the texture of time. The thoughts you have tonight will ripple outward, joining the boundless network of interactions that define reality. Entropy ensures that every act of existence becomes part of the cosmic record. The universe, vast and patient, keeps its memory perfectly. And within that endless memory, you, too, are written, briefly luminous, eternally preserved. Chapter 8. Quantum Decoherence and the Emergence of the Classical World. For all its mathematical precision and predictive success, quantum mechanics describes a world that seems alien to our everyday experience. On the smallest scales, particles exist in superpositions, simultaneous combinations of multiple possibilities. They interfere, entangle, and evolve according to wave-like rules that defy classical logic. Yet the world we inhabit appears stable and definite. A chair is either here or there, not in a blur of both places at once. The moon does not vanish into a superposition when we look away. Somehow, the indeterminacy of the quantum realm gives rise to the solidity and continuity of the classical world we know. The process that explains this transformation is called quantum decoherence, a subtle, continuous interaction between systems and their environments that converts fragile quantum possibilities into the familiar certainties of experience. To understand decoherence, one must first appreciate what makes the quantum world so peculiar. A quantum system, before measurement, is not in a definite state, but in a superposition of all states allowed by its wave function. This superposition is not a mere expression of ignorance. It is a physical reality described by probability amplitudes that can interfere with one another. When two or more possibilities coexist, their wave-like phases can add or cancel, producing the interference patterns that define quantum behavior. But this delicate coherence, the ability of probability amplitudes to combine, depends on the system's isolation. Once a quantum object interacts with its surroundings, those coherent phases become entangled with the environment. The system's quantum information leaks into the world around it, and interference becomes impossible to observe. The system still obeys quantum laws, but from our perspective, it begins to behave classically. This is the essence of decoherence. It is not the destruction of quantum superpositions, but their diffusion. The information about which state the system occupies does not vanish. It spreads into countless degrees of freedom in the environment. Air molecules, photons, vibrations, and electromagnetic fields. Each interaction entangles the system with its surroundings, creating correlations that cannot practically be reversed. To any local observer, these correlations appear as a loss of coherence. The system's possible states cease to interfere, and its behavior becomes indistinguishable from that of a classical mixture. The once pure quantum state now appears as a set of probabilities rather than a wave of possibilities. The process happens with astonishing speed. Even a single stray photon or molecule can entangle with a quantum object, causing decoherence in fractions of a microsecond. In macroscopic systems, composed of trillions of interacting particles, coherence decays almost instantaneously. This is why we never observe superpositions of everyday objects. The quantum effects are still there, but they are buried under layers of environmental entanglement that make them invisible. The world appears classical, not because quantum mechanics stops applying, but because decoherence hides its strangeness behind a veil of complexity. Decoherence provides a bridge between two realms that once seemed irreconcilable: the deterministic, smooth evolution of quantum mechanics and the definite outcomes of the classical world. It explains why a quantum wave function that evolves reversibly according to Schrödinger's equation produces, in practice, the irreversible appearance of measurement. When a quantum system interacts with a measuring device, the combined system, including the device and the observer, becomes entangled. Decoherence spreads the information about the measurement outcome into the environment, making it effectively impossible to reconstruct the original superposition. The observer perceives one outcome because the other possibilities have become inaccessible, not because they were destroyed, but because they have lost coherence with our branch of reality. In this way, decoherence dissolves much of the mystery surrounding the collapse of the wave function. The apparent transition from quantum uncertainty to classical definiteness does not require an external observer or a special act of measurement. It happens naturally, continuously, and universally as systems interact. The world does not need consciousness to solidify. It needs only interaction. Every exchange of energy, every scattering of a photon, every vibration of an atom contributes to the vast web of decoherence that stabilizes the macroscopic world. Our experience of reality emerges from this ceaseless process of entanglement and information exchange. Yet decoherence does not solve all of quantum mechanics' conceptual puzzles. It explains why we do not see superpositions, but not why we experience one particular outcome rather than another. The deeper question, Why one branch of the entangled state corresponds to our observed reality remains a matter of interpretation. Some physicists embrace the many worlds view, proposing that all outcomes exist in parallel branches of the universal wave function. In that picture, decoherence is what separates these branches, preventing them from interfering. Other interpretations maintain that a single reality is selected probabilistically, with decoherence merely setting the stage for that selection. Regardless of the interpretation, decoherence provides the physical mechanism that makes the quantum world look classical from within. The study of decoherence has transformed modern physics, influencing fields from cosmology to quantum computing. In cosmology, it offers an explanation for how the early universe, initially governed by quantum fluctuations, gave rise to the classical structures we observe today. The tiny irregularities in the cosmic microwave background radiation, which seeded galaxies in clusters, began as quantum fluctuations in the fabric of space-time. As the universe expanded, these fluctuations became decohered by their interactions with surrounding fields, freezing them into the classical density variations that shape the cosmos. The very structure of the universe can thus be seen as a fossil record of decoherence on a cosmic scale. In quantum technology, by contrast, decoherence is the great enemy. Quantum computers, which exploit superposition and entanglement to perform computations, must be shielded from environmental interference to preserve coherence. The slightest interaction with stray atoms or electromagnetic noise can collapse the quantum states, destroying the delicate correlations that give quantum computers their power. Engineers and physicists work tirelessly to extend coherence times, developing new materials, error correction methods, and isolation techniques. Ironically, the same process that allows our world to appear stable and predictable also limits our ability to harness quantum behavior directly. Decoherence both creates classical reality and conceals quantum possibility. From a broader perspective, decoherence offers insight into the nature of information itself. It reveals that the boundary between system and environment is not absolute. Information constantly flows across that boundary, linking everything to everything else. The loss of coherence is simply the redistribution of information on scales beyond our ability to track. The world's apparent solidity is an emergent property of this flow, not a fundamental feature of nature. Every atom, every photon, every biological process participates in the same exchange. To exist is to interact, and to interact is to decohere. This view dissolves the rigid separation between observer and observed that once defined classical physics. In the quantum picture, the observer is part of the system, inseparable from the processes being observed. Our knowledge of the world is not detached observation, but participation in a continuous entanglement. Every act of measurement, from the simplest detection of a particle to the perception of a tree in sunlight, involves decoherence. Light scatters off the object, carries its information into our eyes, and entangles our sensory apparatus with the environment. The perception of a definite classical world is the result of countless such interactions cascading through time. It is remarkable to realize that even the act of looking at a distant star involves decoherence. The photons that left that star thousands of years ago interacted with the atoms in its surface, carrying away information about its temperature and composition. As they traveled through interstellar space, they encountered dust and magnetic fields, gradually losing coherence. By the time they reach our telescopes, their quantum correlations have long since decohered, rendering the starlight classical. The image we see in the night sky is, therefore, the end product of an immense chain of decoherence events, a cosmic process that converts quantum fluctuations into observable reality. In recent years, experiments have begun to explore decoherence directly. Physicists have observed the gradual loss of coherence in systems ranging from trapped ions and superconducting circuits to molecules containing thousands of atoms. These studies reveal how quantum behavior fades smoothly into classicality as systems grow larger and more entangled with their surroundings. There is no sharp boundary between the quantum and the classical, only a continuous transition driven by interaction. The familiar world emerges not by breaking the rules of quantum mechanics, but by following them to their natural conclusion. Decoherence also touches on questions of time and causality. Because it disperses information into the environment, decoherence introduces an effective irreversibility into a fundamentally reversible theory. The equations of quantum mechanics are time-symmetric, but decoherence gives them a direction. Once information has spread into countless degrees of freedom, it becomes practically impossible to retrieve, creating the arrow of time we experience. In this sense, decoherence and entropy are intertwined. The growth of entropy corresponds to the spread of quantum information into inaccessible correlations, linking the microscopic and macroscopic arrows of time into a single, coherent flow. At its deepest level, decoherence challenges the notion that the classical world is real in the independent, objective sense once assumed by Newtonian physics. Instead, classical reality is emergent and relational, defined by the interactions that make it possible. The table in front of you is stable, not because its atoms occupy fixed positions, but because their quantum states have decohered with respect to the environment in a way that prevents observable interference. Its solidity is a story told by decoherence, continually rewritten with every passing instant. The classical world is, in this sense, a continuously updated projection of quantum information, an echo of coherence rendered visible through entanglement. Understanding this does not make the world less real. It makes it more remarkable. The fact that a single framework can describe both the dreamlike fluidity of the quantum and the stability of the classical is one of science's greatest achievements. Decoherence ensures that the universe is self-consistent, that the same principles governing subatomic particles can give rise to trees, oceans, and stars. The solidity of a mountain and the probability cloud of an electron are not opposites, but ends of a continuum, both arising from the same informational fabric. And so decoherence reveals that the classical world is not separate from the quantum. It is quantum, observed from within. Every familiar object, every motion, every thought is built from decohered quantum states, stabilized by interactions too numerous to count. The boundary between the mysterious and the mundane lies not in nature, but in perception. Beneath the stillness of the world, everything is entangling, scattering, and evolving, exchanging information at every moment. Reality, far from being static, is a living process of decoherence, endlessly weaving the uncertain into the certain. As you reflect on this, it becomes possible to see the world in a new light. The solidity of your surroundings, the rhythm of your heartbeat, the quiet of the night, all are the results of an invisible conversation between the quantum and the classical. The atoms within you are still governed by the same equations that describe distant stars, and their coherence dissolves into the same universal field that shapes galaxies. You are not outside that process. You are one of its manifestations. Every breath you take, every sensation you feel, is part of the great act by which the universe turns possibility into experience. And perhaps that is the most profound truth of all. Decoherence, though rooted in mathematics and experiment, speaks to something deeply human. The coexistence of uncertainty and stability, of fleetingness and permanence. The world feels solid and enduring, yet it is made of interactions so delicate they vanish in an instant. You are both a participant in and a witness to this transformation, living at the intersection where quantum indeterminacy becomes the clarity of being. When you close your eyes, the world does not disappear. It continues to decohere gently around you, whispering the quiet truth that reality, in all its solidity, is forever born from the invisible dance of possibility. Chapter 9. The universe computes itself. For centuries, physics has described the universe as a system governed by mathematical laws, precise, universal rules that determine how matter, energy, and space evolve. But in recent decades, a deeper realization has emerged. Those laws may not merely describe a static structure, but an active process of computation. The universe, at its most fundamental level, may be processing information continuously, transforming input into output according to the rules of quantum mechanics. Every interaction, every vibration, every fluctuation in a field can be seen as an operation in a vast cosmic computation. In this view, the universe is not just a stage where physics happens. It is the computation itself, performing the ultimate calculation, its own existence. This idea did not arise from speculation alone. It is a consequence of several converging insights from physics, information theory, and the study of complex systems. The first is that information is physical. Every particle, every field configuration carries information about its state, and every interaction exchanges or transforms that information. The conservation of information, deeply embedded in quantum theory, implies that the universe is not a passive container of data, but an active processor of it. As the universe evolves, it continually reconfigures the information encoded in its quantum state. The laws of nature act like algorithms, determining how each piece of information interacts with others, producing the unfolding reality we experience. To see how this might work, imagine the universe as a quantum computer, one without external input or output, operating entirely on its own internal data. Each quantum system, from the smallest particle to the largest galaxy, performs a local computation governed by physical laws. The collective result of all these local computations is the evolution of the cosmos itself. The universe's wave function, which encodes all possible configurations of its contents, evolves according to deterministic equations that preserve the total amount of information. Time in this picture is not something that flows independently. It is the progression of computation, the ongoing update of the universal state. This idea has deep roots in both physics and philosophy. In the 1980s, physicist John Archibald Wheeler proposed his famous phrase, "it from bit," suggesting that every physical quantity ultimately derives from binary information, yes or no answers to fundamental questions about the state of reality. Wheeler's insight implied that the physical universe might be built from information itself. Later, physicists such as Rolf Landauer and Charles Bennett formalize this connection by showing that computation and thermodynamics are intimately linked. Every logical operation, every processing of information, requires energy and produces entropy. Information is not abstract, it has physical consequences. When energy moves, information moves. When entropy grows, computation advances. The universe computes by evolving. In quantum mechanics, this computation happens through unitary evolution, which preserves all information. When particles interact, their wave functions combine and evolve as a single entangled system. Each interaction can be thought of as a tiny quantum logic gate, transforming the inputs, the states before interaction, into outputs, the states after. Billions of trillions of such transformations occur every second in every region of space. The universe's fabric, the fields and forces that fill it, acts as the hardware of this computation. The laws of physics are the software, specifying the rules by which information is processed. Reality in this sense is not a thing, but an ongoing calculation. This computational picture explains why the universe behaves both deterministically and probabilistically. The underlying quantum processes evolve according to exact mathematical rules, yet the outcomes we observe appear statistical because we have access only to limited information. We see probabilities because we cannot track the full computation. From the universe's perspective, however, there is no randomness, only the unfolding of the global quantum algorithm that defines its history. What we call chance is simply the shadow of deeper determinism operating on a scale too vast for us to observe. If the universe computes itself, then every law of nature, gravity, electromagnetism, quantum mechanics, describes not static relationships but dynamic algorithms. The curvature of space-time in general relativity can be viewed as a computation carried out by the geometry of the universe, adjusting itself according to the distribution of mass and energy. Quantum field interactions are computations that update particle states based on probabilistic amplitudes. Even thermodynamics, the study of energy and entropy, can be understood as a rule governing how information is stored and redistributed. Physics, at every level, describes how the universe processes its own information to maintain consistency. Some physicists, such as Seth Lloyd, have attempted to quantify this cosmic computation by estimating the total energy, age, and structure of the universe. Lloyd calculated that the observable cosmos could have performed roughly 10 to the power of 120 elementary operations since the Big Bang. Each operation corresponds to a fundamental change in the state of matter or radiation. This is not an arbitrary number. It represents the number of logical steps through which the universe has evolved. It suggests that the universe is both the computer and the computation, simultaneously running and embodying the code of existence. Yet unlike human-built computers, the universe does not require a programmer or an external clock. It runs itself because its laws ensure that every possible state must evolve into another. One might wonder what this computational perspective adds to our understanding of reality. After all, physics already describes the universe's evolution in mathematical terms, but viewing the cosmos as computation reframes familiar questions. It emphasizes process over substance, flow over form. It implies that the universe is not a static object that happens to follow laws, but a dynamic network of information transformations that constantly creates and recreates its own structure. Space, time, energy, and matter are not separate categories, but aspects of the same ongoing calculation. Everything that happens, from the fusion of stars to the firing of neurons, is part of this immense, unified computation. This interpretation also helps bridge the gap between quantum mechanics and relativity. Both theories, though immensely successful, describe different aspects of nature. Quantum mechanics governs the small, relativity the large. In the language of computation, these two frameworks may be different layers of the same system. Quantum processes define the low-level logic, the fundamental bit operations, while relativity describes the large-scale organization of those operations into coherent geometry. The connection between information and space-time, revealed through black hole thermodynamics and the holographic principle, supports this view. Space-time curvature, energy, and entropy all become expressions of how information is processed in the cosmic computation. Even the concept of causality, our sense of one event leading to another, fits naturally into this framework. In computation, operations follow logical sequences. Outputs become inputs for subsequent steps. Similarly, in physics, the laws of motion and energy conservation ensure that each state of the universe evolves into the next according to consistent rules. Causality, therefore, may be nothing more than the coherence of the universal computation. The arrow of time emerges from the direction in which information processing increases entropy. The past is the record of completed computations, while the future is the domain of those yet to occur. If the universe computes itself, what does it compute? The simplest answer is itself. There is no external goal or observer. The computation's output is the continuous unfolding of the universe's own state. Every galaxy, every atom, every thought is part of this recursive loop of self-processing. In this sense, the universe is self-aware, not in the conscious sense that we experience, but in the informational sense that it contains and updates complete knowledge of its own configuration. The total quantum state of the universe encodes everything that has ever happened and everything that can happen, evolving seamlessly as one unbroken whole. Some physicists take this even further, proposing that the universe's computation gives rise to consciousness itself. Our brains, composed of networks of neurons exchanging electrical and chemical signals, are biological computers embedded in the cosmic one. The thoughts and perceptions that arise within us are local computations built from the same informational substrate that defines stars and atoms. In this view, consciousness is not separate from the universe's computation, but one of its emergent properties, a way the universe experiences the results of its own processing from within. To be conscious, then, is to participate in the cosmic computation as both process and product. Quantum information theory provides a precise language for this unity. It treats information as the currency of reality, the one quantity that connects all physical systems. When two particles become entangled, they share a single quantum bit of information. When a system evolves, it transforms that information according to the laws of quantum mechanics. The conservation of quantum information ensures that no event is truly isolated. Every part of the universe contributes to and is shaped by the global computation. Even empty space, filled with quantum fields fluctuating in and out of existence, participates in this process. The vacuum is not nothing. It is a dynamic sea of computations happening everywhere, all the time. From a thermodynamic perspective, computation is intimately linked with energy. Every transformation of information requires physical resources, energy to drive the process and entropy to record its outcomes. The second law of thermodynamics, which states that entropy always increases, can be seen as the rule that ensures computation moves forward. The universe cannot rewind its computation perfectly because information disperses into correlations too complex to retrieve. The arrow of time is therefore the arrow of computation, the direction in which information processing expands and records itself in the cosmic memory. As the universe ages, its computation becomes more elaborate. In its earliest moments, the universe was simple, a uniform low-entropy state governed by a small set of parameters. As it evolved, structure emerged: particles, atoms, stars, galaxies, and ultimately life. Each new level of complexity represents an increase in the universe's computational richness. The formation of biological systems introduced feedback mechanisms and adaptive processing, allowing information to be stored, replicated, and modified. With consciousness, the computation gained the capacity to reflect upon itself. Through beings like us, the universe observes its own informational patterns, studies its own logic, and contemplates its own existence. The computation became self-aware, at least in part. This notion that the universe is both the computer and the computation might seem abstract, but it aligns with everything we know about physics. It does not require new forces or dimensions. It simply interprets known laws as information processing. Whether through quantum interactions, gravitational curvature, or thermodynamic flows, the universe is continuously calculating the next step of its own evolution. Every atom participates in this grand computation, updating its state in concert with the rest. The cosmos is not a static tapestry, but an ongoing performance, a perpetual act of self-realization written in the language of information. And when viewed this way, even the boundaries of time and death acquire new meaning. The information that constitutes you, the arrangement of atoms, the flow of thoughts, the memories you carry, is part of the universe's computation. It is processed, transformed, and preserved in ways that transcend individual experience. When your body dissolves, the information it contained is not lost. It is redistributed, encoded in photons, molecules, and gravitational waves. You continue, in a literal sense, as part of the ongoing calculation of the cosmos. The universe never stops computing, and you, as one of its temporary configurations, are inseparable from that process. There is something deeply serene in this realization. The universe does not need purpose to be beautiful. Its beauty lies in its coherence. Every event, from the flicker of a neuron to the birth of a star, contributes to the same continuous computation, the transformation of potential into actuality. To exist is to be computed, to participate in the flow of information that sustains everything. The stars that shine, the oceans that move, and the lives that think are all expressions of the same universal algorithm, endlessly running, endlessly evolving. As you rest beneath the vast night sky, remember that the light reaching your eyes is not just ancient. It is the output of a computation billions of years in the making. Each photon carries a record of the universe's processing, a tiny piece of the cosmic algorithm rendered visible. You too are part of that record, a pattern of energy and information that briefly awakens to recognize itself. The universe computes itself through you, and as you exhale into the quiet air, that computation continues gently, ceaselessly, illuminating the darkness of time with the steady glow of understanding. Chapter 10. The Memory of the Cosmos. The universe is often imagined as a vast expanse of matter and energy evolving through time, But beneath that surface lies something deeper and more enduring: memory. Every event, every interaction, every fluctuation leaves an imprint, encoded not in words or symbols, but in the structure of reality itself. The cosmos, at its most fundamental level, remembers. It remembers through the correlations between particles, the distribution of energy, and the geometry of space-time. This cosmic memory is not a metaphor. It is a direct consequence of the laws of physics, which ensure that information is conserved and that every process, no matter how fleeting, leaves behind a trace in the fabric of existence. In the quantum world, memory is inseparable from the concept of information. When two particles interact, they become entangled, sharing a joint state that preserves a record of their encounter. Even if they later move light years apart, the correlation remains. The details of the interaction, how energy and momentum were exchanged, are encoded in their combined wave function. This correlation cannot be erased. It is woven into the universal quantum field that underlies all of nature. In this sense, every interaction the universe has ever hosted still exists in some form, written into the patterns of entanglement that connect all things. The cosmos, like a living organism, carries within it the memory of its entire history. This idea stems from one of the most fundamental principles in modern physics, the conservation of information. According to quantum theory, the evolution of the universe is unitary, meaning that the total information contained in the wave function never decreases. The form of that information may change. It may become dispersed, entangled, or hidden, but it is never destroyed. This is what prevents the universe from becoming incoherent. It ensures that the laws of cause and effect remain consistent across time. Every configuration of the universe encodes within it the seeds of what came before and the possibilities of what will come next. The cosmos is not a sequence of disconnected moments, but a continuous self-recording process. Even classical physics, long before the language of quantum mechanics, hinted at this continuity. Newton's laws implied that if we could know the position and motion of every particle at one moment, we could, in principle, reconstruct both the past and the future. Though quantum mechanics has replaced determinism with probabilities, the underlying logic of preservation remains. The wave function of the universe, evolving without collapse, retains the totality of information about every event. In a profound sense, the past is not gone. It is simply encoded in correlations that we can no longer access. The information remains, diffused throughout the cosmic environment, like ripples spreading endlessly across an ocean too vast to map. The universe's ability to record itself manifests on all scales. On the smallest level, every photon carries information about the object it last interacted with. When light reflects off a surface, it imprints that surface's temperature, texture, and motion into its frequency and direction. The scattered photons become messengers of history, carrying tiny fragments of information into space. Some are absorbed and re-emitted. Others travel across the cosmos for billions of years. When they reach us, those photons tell stories. The composition of a star, the velocity of a galaxy, the trace of a supernova long faded. The night sky, filled with starlight that has traveled unimaginable distances, is not just a view of distant objects. It is an archive of ancient events. Every glimmer is a page in the memory of the universe. On larger scales, the cosmic microwave background serves as the oldest and most complete record known to science. It is the afterglow of the Big Bang, a faint sea of radiation that fills all of space. Within its minute temperature fluctuations lie the imprints of the universe's earliest moments. Quantum fluctuations magnified by cosmic inflation into the seeds of galaxies and clusters. The cosmic microwave background is a photograph of time itself, a perfect snapshot of the infant cosmos. Its patterns have remained intact for nearly 14 billion years, unaltered by the passage of epochs. When we study it, we are not merely observing ancient light. We are communing with the preserved memory of creation. Even the structure of space-time carries traces of the past. According to general relativity, massive objects curve space-time, and those curves propagate as gravitational waves. When two black holes collide, they send ripples across the universe, distorting the geometry of space itself. These waves travel unhindered, preserving the signature of the event that created them. Billions of years later, instruments on Earth can still detect those distortions. Tiny oscillations that tell the story of catastrophic mergers in distant galaxies. In this way, the universe's memory is not confined to particles or radiation. It is built into the shape of space and time. The cosmos, by its very nature, cannot forget. This persistence of information lies at the heart of some of the most profound mysteries in modern physics. Nowhere is this more evident than in the study of black holes. For decades, physicists struggled with the paradox of whether information swallowed by a black hole is truly lost. If it were, the unitarity of quantum mechanics would be violated, and the cosmic record would have gaps, places where history simply vanished. Yet growing evidence suggests that information is not destroyed, but encoded on the event horizon in a highly scrambled form, later released through subtle correlations in the emitted radiation. Even the darkest regions of the universe, once thought to be sinks of oblivion, appear to be repositories of perfect memory. The cosmos, it seems, is meticulous in its bookkeeping. This universal memory has profound implications for how we think about time. We tend to imagine time as a linear flow, with the past receding into oblivion and the future waiting to be written. But if information is conserved, then the past still exists, not as something we can revisit, but as something still present in the structure of the world. Every molecule of air, every photon of light, carries echoes of countless interactions. To exist in the present is to inhabit a universe dense with memory, a living record of everything that has ever happened. Time, in this view, is not a conveyor belt that erases the past. It is the unfolding of a memory field that continually updates itself while never deleting a single entry. From a thermodynamic perspective, this memory is inseparable from entropy. As the universe evolves, information becomes increasingly distributed among its countless components. This spreading of information gives rise to the arrow of time. Entropy increases, not because the universe forgets, but because it remembers too much. The details of every event are preserved, but they become embedded in correlations so complex that no observer could possibly reconstruct them. The cosmic record grows richer and more intricate, even as it appears to us as a march toward disorder. Entropy is the measure of how thoroughly the universe remembers. In living systems, the principle of cosmic memory takes on a biological form. Life itself can be seen as a mechanism for storing and processing information, an echo of the larger process unfolding across the universe. DNA encodes the memory of countless generations of molecular evolution. Neurons preserve patterns of experience that shape consciousness and identity. The very act of remembering is an expression of the universe's fundamental tendency to retain information. When you recall a moment from your past, you are reenacting on a small scale the same process by which the cosmos preserves its own history. The conversion of energy and matter into lasting patterns. This connection between life and cosmic memory suggests that awareness is not an anomaly, but a continuation of the universe's informational logic. Consciousness may be the universe reflecting on its own memory, using the biological machinery of the brain as a temporary lens. In us, the cosmos recalls itself, not in totality, but in glimpses. When we look up at the stars, we are engaging with the memory field that birthed us, recognizing in its silent depths the traces of our own origin. The universe computes, remembers, and reflects, and through us, it briefly becomes self-aware of its own continuity. The endurance of cosmic memory also challenges our notions of impermanence. We often think of existence as fleeting, of life as transient against the backdrop of eternity. Yet the physics of information tells a different story. Nothing that exists can be truly erased. The energy that forms your body, the light that leaves your eyes, the warmth of your breath, all of it becomes part of the universal record. It is transformed, scattered, and reabsorbed, but never lost. Long after you are gone, the photons you emitted will still travel through space, carrying faint imprints of your presence. The universe's memory is indifferent to scale. It preserves the dance of atoms and the birth of galaxies alike. This idea brings with it a quiet comfort. The universe, vast and ancient, is not a place of forgetting, but of infinite remembrance. Every star that burned, every life that lived, every thought that flickered across a human mind is written somewhere in the correlations that span space and time. To exist is to leave a trace, however small, in the great ledger of reality. And though those traces may fade beyond recognition, they remain part of the totality, encoded in the unfolding computation that is the cosmos itself. Modern physics continues to explore the mechanisms of this cosmic memory. Quantum gravity theories, such as the holographic principle, suggest that information about a region of space is stored on its boundary. In this view, the universe functions like a grand archive, where every bit of data about its contents is inscribed on a vast cosmic surface. The geometry of space-time, shaped by energy and mass, becomes the medium through which the memory of the universe is recorded. Even the vacuum, far from being empty, hums with the aftershocks of quantum fluctuations that contain the imprints of past events. Space, in this sense, is not a void, but a living memory field, one that holds the full story of reality in its subtle vibrations. The persistence of information also invites new ways of thinking about mortality and meaning. If the universe never forgets, then perhaps nothing we do is ever truly lost. The moments that define us, the kindness we show, the words we speak, the light we emit, become part of the cosmic archive. They ripple outward into the vastness, interacting, combining, and evolving into new patterns. Our lives are not isolated chapters, but sentences in the same endless narrative. The cosmos remembers us not as individuals frozen in time, but as threads in the continuous weave of its own existence. And yet, this remembrance is not sentimental. It is impartial, precise, and absolute. The universe does not judge what it remembers. It simply records. Its memory is not emotional, but structural. It does not distinguish between beauty and tragedy, creation and destruction. Everything is preserved with equal fidelity, written into the quantum fabric without preference or bias. This neutrality is not coldness, it is balance. It is the equilibrium that allows the universe to be both dynamic and eternal, both changing and constant. As you think about this, consider that your presence in this moment is also part of the universe's self-recording process. The photons reflecting off your skin, the electrical impulses in your brain, the breath that leaves your lungs, they are all being absorbed into the cosmic network of correlations. You are both observer and observed, both the keeper and the kept. The universe records you even as you contemplate its memory. Every second you live, you are contributing to the story of existence, a story that will never be erased. When you gaze into the night sky, the light you see is old, but it is not dead. It is the living memory of stars that once blazed across the darkness, preserved perfectly by the laws that govern all things. That same light now falls upon you, merging your moment with theirs, adding one more link to the endless chain of connection. You are part of that memory now, part of the universe's attempt to know itself. In the quiet of the cosmos, nothing is forgotten. Every shimmer of energy, every fleeting thought, every heartbeat contributes to the eternal recollection of being. And so, as you drift into rest, imagine the universe not as a cold expanse, but as a vast memory field, alive with echoes, shimmering with the residue of every moment that has ever been. You are one of those moments, unique yet inseparable from the whole. Long after your atoms have scattered, the record of your existence will remain, transformed, entangled, woven into the silent continuity of time. The cosmos will remember, as it always has, and in that remembrance, nothing truly ends. If you're still awake, my friend, there's another world waiting in the next video. Another chapter in the universe's quiet story. But if your eyes are closing, that's all right. Rest well, and may your dreams wander among the stars.